Get started. Let's continue with our public lectures. So it's a great pleasure to have Gabriela Gonzalez telling us about gravitational waves. So Gabriela is from Argentina, and she left Argentina roughly 20 years ago, and she is at State University in Louisiana, and she will tell us about something that for me looks like science fiction, but which, thanks to people like her, is now part of science. So thank you very much.
Thank you. It's a big pleasure to be here. This is my first time giving a talk and actually staying in the city of Sao Paulo. I've been in the state and I've been in Brazil many other times before, but it's very nice to be here, especially talking to you about gravitational waves, which has been the passion of many people for many years. This is a really long story, and in fact it begins about 1 billion years ago. Let me see if I can make this work. When two black holes were dancing a tango, as I like to think, perhaps samba, and they were rotating around each other, around the center of mass of the black holes, and they were losing energy. They were distorting the fabric of space-time and generating these waves that were carrying energy away until they, moving at almost the speed of light, they fused into a single larger black hole that then settled down and stayed quiet. But these gravitational waves began traveling throughout the whole universe. This sounds like science fiction, like Pedro was saying, but it's not. It's real. We know it happened because we've seen these gravitational waves go through Earth last year. Now, you heard in the previous lecture how about Einstein 100 years ago. So now we move from 1 billion years ago, when on Earth there were multicellular organisms, through the evolution of humankind, the Industrial Revolution, the Scientific Revolution. 100 years ago, the theory of general relativity, when Einstein explains the gravitational forces as not forces but distortions of space-time that make these stars, like these black holes, move and distort the space-time, producing these gravitational waves. Now, he predicted that, and as you heard, also several other effects that were measured. So we knew his theory was correct. But this particular prediction is something that we really, really wanted to measure. And we knew about this. Again, we knew a lot about proving Einstein relativity, even from 1919, with measuring the bending of the light from the stars in an eclipse. But we also learned about gravitational waves a lot some time ago, in the 70s. In the 70s, in fact, earlier in the 70s, there had been some stars discovered that emitted radio beams. So emitted radio waves in a very beamed fashion. These are called pulsars. And we know they exist because these are stars that are very, very compact. It's like the mass of the sun in Sao Paulo is too big, in the size of about a quarter of Sao Paulo. So you compress all of the mass of the sun in that small space, about 10 kilometers, in a very, very spherical fashion. You make this star rotate very fast and emit a radio beam like a beacon. It's not, the beam is not emitted in the same direction that the star is rotating. So the star is emitting this radio beam, this signal, and here on Earth, if we are lucky, sometimes we see these radio blips. And in fact, it was a graduate student in the UK, Jocelyn Bell, who saw these radio beeps that were so regular, that first she joked that these could be little green men. And this LGM stuck for a while as an explanation, but in fact it was soon discovered that it was a signature of these pulsars, these neutron stars. In the early 70s, so that was in the 60s. In the early 70s, there was another graduate student, Hulse, working with a very famous astronomer. Well, he became very famous a bit later, Joe Taylor. And they wanted to find a binary system. They wanted to find one of these radio emitters, one of these neutron stars that had a companion, and even if it would be better if that companion was also a neutron star. And the way you do that is measuring these blips, these radio blips, which are very, very regular, but sometimes they get a bit faster and sometimes a bit slower, and sometimes a bit faster and sometimes a bit slower. And that would be because the star would be rotating around another star. So from the radio blips of this star, you can tell that there is another star. And they discovered this, the first binary neutron star system in the 70s, but it also happened that these two stars were relatively close. The period of rotation was only 8 hours. In 8 hours, you have these two solar masses going around once. Imagine the velocity of this. And they were emitting these gravitational waves. And they saw the prediction from Einstein's theory is that these stars were going to get closer and closer together. In fact, the prediction would be that the stars would merge into a black hole, and then space-time would be distorted because there is a black hole here and because these gravitational waves again are traveling away. And this was, in fact, measured, as I mentioned, by Hulse and Taylor, measuring for many, many years, although Hulse was the graduate student who did the initial work, then it was Taylor and Weisberg who kept going and measuring how far apart these stars were. And they were getting closer and closer together, just like Einstein predicted. If you look at this, this is a quantity that's proportional to the distance between the stars. These are years. Notice that this starts in 1975, it ends in 2005, 30 years of measurements. And the prediction of Einstein's general relativity is beautifully coincident with the measurements. This is one of the best tests of general relativity and the existence of gravitational waves. So we didn't discover gravitational waves. We knew they existed. We measured the effect on space-time. How could that be measured? When did that start? It started actually in the 70s, also when these discoveries about pulsars were being made. There were also people, Ray Weiss at MIT, talking with Kip Thorne in Caltech about ways. Kip Thorne was very enthusiastic about black holes and space-time, and Ray was thinking about how to measure things with high precision, and they thought it would be a great idea if Caltech and MIT got together to measure gravitational waves. Caltech hired Ron Driver to try to put this all together. So this was in the 70s. It took a while. What they had in mind was constructing two observatories that could measure gravitational waves with interferometers. Now, how many of you know how an interferometer works? Okay, about a third. That's very good. That's very good. Let me tell you anyway. An interferometer is a way to measure very, very precisely differences in distance. So you don't measure one distance, you measure the difference between one distance and another. And the idea is to have a laser that emits light. It doesn't have to be a laser. Actually, Michelson and Morley first used this device in the 1880s, and it was just a source of light. So you have light that comes to a beam splitter. A beam splitter will make the light split in two, one going this way, another going this way, and this one will go to that mirror, and this one will go to that mirror. And then what happens? Well, these mirrors are going to bounce the light back, and the beams are going to meet here again, but this beam is going to split half this way and half that way. this beam is going to split half this way and half that way. And let me show you what happens. So that's the light, it splits, it comes back, and then the beams that come this way can interfere constructively or destructively. So we may have no light here, or we may have some light. And that depends on the difference in distances between this arm of the interferometer and that arm. So these are the waves, the electromagnetic waves. Here they're interfering destructively, so there's no light. But if these distances change, then there might be light. So if we put a photocell here, a photodiode, and we measure how much light there is in here and how it changes, we can tell how these two distances are going to change. That is the idea of an interferometer. We can measure changes in distance, and we can do it very precisely because we can measure it as a fraction of the wavelength. The wavelength of a laser is small. We use an infrared laser. It's a micron, so we can measure as a fraction of a micron. So how good these measurements had to be? What do gravitational waves do? Well, they distort space-time, they change distances. What we might have had in mind is that gravitational waves...
It reached Earth.
In a very exaggerated way, could come through Earth, and then they would change distances. They could change the radius of the Earth. They could change the radius of cylinders. They change all distances. And then if the gravitational wave is big, and then it settles down, it could have made the Earth ring down. Could we measure that? Well, of course, we knew that the Earth wasn't ringing up and down all the time, so these gravitational waves were not strong. In fact, in the 60s and the 70s and the 80s, people tried to measure gravitational waves with cylinders, metal cylinders that would ring up if there was a gravitational wave going through. And those were very sensitive. So how do we measure the amplitude of a gravitational wave? We don't measure it as the motion of a particle. We do not say this particle is going to move a micron or a tenth of a micron. What we say is this distance is going to change. And we cannot say how much this distance is going to change. What the amplitude of the gravitational wave tells us is the fractional change in distance. So if this distance changes by this much, the same gravitational wave will make this distance change by twice as much. The change in distance is proportional to the distance. So the longer you measure, the longer the distance you measure, the better, the easier it's going to be. Again, how small do we need these things to be? Well, initial calculations were that for two neutron stars, well, first, how often these things happen. Two neutron stars like these discovered by Hulse and Taylor, you would measure them, the gravitational wave would be the largest when the stars are just before the merger. That merger only happens about once in 10,000 years in our galaxy. So that's way, way too long to wait. Supernovas already take too long. 10,000 years is too much. So we would need to measure farther away. So we imagine, well, let's see if we could measure these things happening in the Virgo cluster. There are many galaxies there. These things would happen once every 50 years or so. How big are those waves? Those waves from two neutron stars coalescing just before coalescence is a fractional change of distance of 10 to the 21. 10 to the minus 21. That means that the change between the Earth and the Sun changes by an atomic diameter. And we can't measure the distance between the Earth and the Sun with that precision. This would also be at a few hundred hertz, near a kilohertz, near about 1,000 times per second. But these people in the 70s, Ray Wise and Kip Thorne, and well, Kip Thorne was a theorist, but Ray Wise and Von Driver said, we can build things that can measure that if we build them kilometers long. On kilometers long detectors, we would be measuring a lot less than an atomic diameter, because the change again is proportional to the distance. So we would be measuring, we would need to measure a part in 1,000 of a proton diameter. So their idea was to use interferometers that would have kilometers that way, to measure changes in these two distances that were not just subatomic, but subnuclear. They actually had a conceptual design with pen and paper that could work. There was also more proof of the amplitude of these gravitational waves. I'm going to be going back and forth in the story just to show you how much it took. There was a lot of work on calculating what the gravitational waves would look like. We knew that, for example, for these neutron stars, when they are going around, they would look like sine waves that get a bit larger in amplitude and frequency. But near the merger, which is what we wanted to measure, we don't know, because when neutron stars merge, then there's a lot of nuclear physics and radiation, and it's a big mess. And there are people trying numerical simulations, but they are very, very complicated. So perhaps something simpler, perhaps black holes. Black holes don't have any matter structure outside the horizon, and the only things that we see are outside the horizon. So these, if we could see what black holes do when they get closer together and merge into a single larger black hole, then perhaps we could have a very nice waveform to look for. That actually took a long time. It was only in the 2000s when people in numerical relativity were able to calculate, to simulate space-time. So this is a very nice simulation that shows the curvature of space-time near two black holes. So it shows how the two black holes are getting closer together. Let me see. They are getting closer together. This is a time before coalescence, so this is 0.3 seconds before the two black holes merge into one. And this was a simulation of two black holes that were about 30 solar masses each, similar in mass. Each was distorting space-time quite a bit, very near the black holes, but then they could also calculate how much distances were going to be distorted far away from the black holes. They could also calculate gravitational waves that we could perhaps measure on Earth. So this is the gravitational wave that we would measure, and as you can see, when the black holes are going around each other, it's like a sine wave. But then, as they get closer, then the frequency is higher, the period is shorter, because they are going faster and faster. This is 0.1 seconds before merger. Now the curvatures are almost there, and here we slow down the movie. This thing actually accelerates. Now the horizons are getting very close, and then it's a big mess in here. As the black holes merge, the curvature here, it's up and down and sideways, and this is in all 3 dimensions. We're plotting it in 2 dimensions, but this is all happening in 4 dimensions, in space and time. But then after the merger, the black hole is quietly rotating. It's there, quietly rotating, and these gravitational waves are taking the information about this final embrace of the 2 black holes. Now, if we look at what we would measure here on Earth, we see that again, these sine waves are getting larger in amplitude, closer together, so a shorter period, a higher frequency, and then after the merger, it just settles down. And we can also calculate, or they, the people who do these simulations, they can also tell us how big these final amplitudes are going to be. and 2 black holes, 30 solar masses each, a billion light years away, would produce here on Earth a fractional change in distance of about 10 to the minus 21. Same as neutron stars near in the Virgo cluster at 15 megaparsecs away. So, could we measure this? Well, we go back in history a bit. In the 90s, before these numerical simulations were done, but after we knew about gravitational waves existing and we knew more about general relativity, the National Science Foundation in the US and other agencies in other countries, but in the US, the National Science Foundation decided to fund 2 detectors, each one 4 kilometers long, one in Louisiana, in Livingston, Louisiana. This is very close to where I live. You can see a big logging forest in there. If you looked a bit farther, there's a swamp and the Mississippi River. And 3,000 kilometers away, the LIGO Hanford Observatory in the middle of the desert. So 2 observatories, 3,000 kilometers away, 4 kilometers long each. This was a big investment. It's even bigger and more and riskier if you think that at the time this was made, the technology that was known and was going to be installed in these observatories was known to deliver noise of about 10 to the minus 21. So the noise that you would see out of the detector was about 10 to the minus 21. So that was not enough to see a gravitational wave of 10 to the minus 21. But funding agencies knew that. What they wanted to do was fund a facility, an observatory, test the technology to make sure that you could measure this kind of precision. That sounded impossible. Many people did not believe it could be done. And then, in the years that took to install that technology, that was known to be about 10 years or so, use better technologies to install a second generation that would then detect gravitational waves. I think some people were counting on being lucky the first time too. At least I was, but we weren't lucky with the initial generation of LIGO detectors. There were 2 LIGO detectors built in the US. There was a Virgo detector from the Virgo European collaboration in Italy. We all took data for several years until 2010. We did not detect gravitational waves, but like I told you, in 2008, there was this approval for better technology. And I'm not bothering telling you about the initial technology. This technology that we have in advanced LIGO is just amazing. I'm an instrumentalist. David Gross told you about the beauty of theory, and I appreciate the beauty of theories, but I have to say, when you look at these experiments and how much it takes, not just of technology, but people working together to get all of this precision, it's just beautiful. So this is a Michelson interferometer I showed you. These lasers are actually high-power lasers that have to be stabilized in frequency and amplitude, so they're very non-trivial. They have to travel in vacuum, because in air, of course, the beam doesn't travel straight. So that's a vacuum tube that has 1.2 meters in diameter inside a concrete enclosure. That's why from the air you only see this concrete enclosure that looks like a tunnel. This is the largest vacuum systems in volume in the Earth, and this is ultra-high vacuum. The vacuum was set in the 90s, and only a few years ago there were some very small leaks discovered that have been fixed since then. The mirrors are not just mirrors that you boil down to a table, because you don't want the mirrors to be moving. So a way to make a mirror not move at certain frequencies is to suspend it from a pendulum. If you suspend a mass from a string, that's a pendulum, and then you know that if you move the support point very slowly, then the mass is just going to follow. So you're not suppressing any motion. If you make the support point move at just the right frequency that we call the resonance frequency, then the pendulum goes like this. And we don't want that, so we have to push on the mass so that it doesn't move that fast. But if the support point moves much faster than that resonance frequency, then the pendulum doesn't move. And the faster this moves up here, the less the pendulum is going to move. So you are suppressing the motion of the ground, of the support point, at frequencies that are higher than the frequency of the pendulum. So we have pendulums that have about 1 hertz, 1 cyclosecond, or lower frequency. And then what we do is not just have our mirror hanging from 4 fibers, which are glass fibers, but we also have this mass hanging from another mass, hanging from another mass. So you multiply that effect. We have a quadruple pendulum. And that's not enough. You have to make all of that hang from a seismic isolation platform that has 3 layers in which we measure the relative motion of the layers and we cancel it. That's active seismic isolation. And all of that, this pendulum hanging from this platform, is all in a vacuum chamber. And the mirrors that we have are big mirrors because we want the beams, the laser beams, to be really big so that they can average over lots and lots of atoms on the face of the mirror, because the atoms in the mirror are all going like this. They are at room temperature, they're all vibrating. That's called Brownian motion. Brownian motion that Einstein had a theory for in 1905. And they are moving, so we want to average over all that motion. And we have several ways of being more insensitive to that. So we have to put all of that together. We have to take care of every mirror being controlled. And it's even more complicated than that, because we not only have these mirrors suspended at the ends, we also have the beam splitter suspended, and in the way from the beam splitter to the end, we put another mirror in here so that the light goes back and forth many times. And that's like making the interferometer longer. That makes us more sensitive because it's like a longer effective distance for the interferometer. So this is called a Fabry-Perot cavity. We had a Michelson interferometer. We actually operated in such a way that out of the interferometer, the interference is destructive, so there is no light coming out, which means that the beams that are going back to the laser have constructive interference. So there is a lot of light going back to the laser. So this whole thing is acting like a mirror. So we take advantage of that and put another suspended mirror in front of that to make the light go back and forth. That's called power recycling. We recycle the power that's trying to get back to the laser. And in fact, in advanced LIGO, we also use signal recycling. If there's anything that comes out, we send it back. We have to push on all the masses so they are at the right distances for this to work. Operating this system is very, very complicated. It takes years to improve the sensitivity, not just to put every mirror and to install all the hardware, but also to make it work at the level that you think it should work, limited only by the quantum noise in the light at high frequencies, by the seismic motion through the pendulum at low frequencies, and by the Brownian motion at intermediate frequencies. What we have is some noise out of the interferometer. We measure how much noise we have, and then we keep it beating it down until we know it reaches some fundamental limit, and that's our best detector. We have achieved the sensitivity, and with advanced LIGO, we knew that with that sensitivity, we were going to detect gravitational waves. In 2015, we had installed our hardware. We had begun measuring noise in both the Hanford and Livingston detector. It wasn't as low as we wanted it to be, so we still have another factor of 3 or so in beating the noise down, but we had already planned from the beginning that as soon as we reached a decent sensitivity that was about 2 or 3 times better than it had been in the past, we were going to take data for a while, and then stop and analyze the data, improve the detector, and then start again. So this was going to be something that we repeated once a year. But as you probably all know, we started taking data in September, and on September 14, 2016, just a bit more than a year ago, we saw this. And this has been the sweetest but largest surprise in our lives, even for people who have been working on this 40 years. So with just minimal filtering of the noise in Livingston, we saw a signal. This is just noise, but then we begin to see something that looks like a sine wave, and then we see that it grows in amplitude, but it also gets short, the period gets shorter, and then it gets larger, and then it settles down. That's exactly what we expected from a binary system coalescing into one. In Hanford, doing the same minimal filtering, we see almost the exact same thing, except that it's shifted by 7 milliseconds. Now, the two observatories are 3,000 kilometers away, so the light would take 10 milliseconds. The light or a gravitational wave would take 10 milliseconds if it goes straight from one to the other. If the gravitational wave is coming from any other direction, we should detect it in the two observatories with less than 10 milliseconds difference. And to make these two signals be on top of each other, we had to shift them by 7 milliseconds. For us, near the Livingston detector, we were very happy that it came first through Livingston, but of course it doesn't matter. So this looked like a gravitational wave. But we had just started taking data with our detectors. Could this be real? I mean, we couldn't really believe it. The first thing that we thought is, well, somebody injected it. We were doing lots of tests, pushing on the mirror, simulating gravitational waves. Somebody simulated a gravitational wave and forgot to write it in the log. We have an electronic log. So we called lots of people. We looked at lots of channels. No, that was not the case. So that took a few hours to convince, at least me, but other people were not convinced for weeks. So it wasn't a simulation, it was something in the detectors. Could it be? We know that the detectors, in the detectors, when you look at the noise, sometimes you see big things that are above the noise in the data. Most of the times you see it in one detector but not in the other, so you know it's not a gravitational wave. But could this be something that happens in the detector so often we didn't notice because we just began taking data, and it happened just to laugh at us? It happened at the same time in both detectors? We didn't know. That it was a crazy scenario, but we had to convince ourselves. So we froze the instrument in case that this was produced by some loose cable or something. So we froze the instrument, we didn't let anybody get close, and we took data for a few more days in that frozen state to see if the instrument was doing this all the time, and it wasn't gravitational waves. The instrument didn't do that. We said, well, we need to take more data now to have statistical confidence on this. And we had just begun taking data. We were planning to take data for 3 months. We didn't want to wait 3 months. We knew it was going to take us some time, but we didn't want to analyze all of 3 months' data before beginning to vet this. So we said, well, we are going to take 1 month of data, and if everything goes well, we'll go through the whole process we have for vetting a discovery. We're going to find out about all seismic stations in the world, or weather stations in the world, all channels. We have thousands and thousands of channels in the interferometer to make sure that this can only be caused by a gravitational wave. It took us several months to convince ourselves. write an article, send it to publication for experts who were not in our collaboration to tell us whether we had forgotten something. They didn't find anything we forgot, so in February 11 of this year, we announced we did it. So that was a very, very emotional moment in Washington. Ray Wise was playing with pendulums in there. I hope you have seen that press conference. If not, you can go to YouTube and look at it. I think it was fun. It was fun, and it's not that long. But it created waves all over the world. Waves, of course, in papers, and people like sometimes showing the New York Times, but I found for this talk local papers. This is, I think it's one of the biggest local papers in Sao Paulo. And you can tell that there are some issues that are very important. But the largest picture in the first page was that of Kip Thorne and Ray Wise with the universe behind it. And this is one of my favorite covers all over. El Señor del Universo, Señor del Universo. I love that cartoon. But it wasn't just in newspapers, and it wasn't just in the scientific world. It was in the general public. Something we discovered not that long afterwards is that there's a company, Shinova, actually it's mostly a woman who makes dresses with technological motifs, and she took our waveform. That's our waveform. I have that dress. It doesn't look as nice on me as it does on her. But it affected, there are donuts with the waveform, there are people who tattooed the waveform, actually more than one person tattooed the waveform. It just has created a lot of sensation in the general public as well in the scientific public. But who is we? I just want to make sure you understand that. We is the people who had to build, first had the vision to build these instruments and were persistent enough to convince funding agencies, again, not just in the US, but in Europe and other countries, to build these instruments, to take data, even though it was unlikely to happen in the beginning. It was known to take many years. All the people who analyze the data, who invented the methods to analyze the data and deal with all this very noisy data, there are thousands of us. In fact, the LIGO Scientific Collaboration that I lead has 1,100 members from more than 90 institutions, some here in Brazil. Actually, Brazil is the only Latin American country so far in this collaboration. And we work together with the Virgo collaboration, which is at 250 people too. So we is a lot of people because it takes a lot of people, physicists, engineers, senior people, younger people, technical operators, lots and lots of people to work together to do this. And a lot of time. I mean, this started with Einstein. This was Joe Weber with the first detectors. It took a lot of time until we got to that embrace of Kip and Ray. And there are lots of groups all over the world. This is a group in INPE with Ogilio Diar, Cesar Costa. This is Ricardo Sturani here in Sao Paulo. So we have people in 16 different countries, including Brazil, working on this. Okay, let me go back to the science. I told you about that first detection. That first detection, from the frequency, we could tell that the masses were 29 and 36 solar masses. That we can tell from the frequency. We could tell how far away they were from the amplitude of the wave. That was about 1.3 billion light years away. And we could tell that when they coalesced, they formed a black hole that had 62 solar masses. Now, 29 plus 36, for those who do algebra in their head, is not 62. There are 3 solar masses missing. That's mass that got converted into energy of gravitational waves. Einstein says that E is equal to mc squared. Energy and mass can be transformed into each other. 3 solar masses, 3 suns got converted into energy of gravitational waves. That's a huge amount of energy. So gravitational waves produce a small effect in distances, but they carry a lot of energy. But that wasn't the only thing we saw. We kept taking data. Like I told you, we had planned to take data for 3 months. Then we decided, well, let's take data through the holidays. We won't be able to change the detectors anyway until January. And on December 26th, Universal Time, which was December 25th in the US and in America, so we had a Christmas gift. We had another detection, very, very, very significant. It's not as large, so I cannot do that filtering, that nice filtering I showed you to show you the cycles. It's just hiding more in the data, so we had to use what we used for the first signal too. We had to use our data analysis methods to find the signal and to prove that it was statistically very, very significant. But this is another detection. This is our second detection. In this one, the 2 black holes are smaller. This one is 8 solar masses. This is 14 solar masses. This was at 1.3 billion light years away. This was 1 billion light years away. These were 7 milliseconds apart. This was 1 millisecond apart. So they are similar, but different. And that's very good, because that means that this is a real observatory. We will be measuring many of these signals from now on when we have the detectors on. We even had a third, some people call it signal, some people call it candidate. I like to call it candidate. When we do the analysis, there seems to be a coincidence on October 12th that is also consistent with the coalescence of 2 black holes of intermediate mass, not as large as this one, but not as smaller as these ones. So it looks like a good member of the family. But if we had only looked at this signal, there's no way we could tell that's a gravitational wave or that it's coming from black holes. We only suspect it's real because it has these other very, very strong ones. But again, this is proof that we are measuring gravitational waves. Now, I didn't show you a spectrum of the noise of our detector, but because we have noise at low frequencies from seismic noise and noise at high frequencies from quantum noise, then we have one sensitive frequency band. We can only measure gravitational waves of certain frequencies. It turns out that those frequencies, which are around 100 hertz, are frequencies that if you put signals in a speaker, you can hear. So we like to say that we can hear the universe. Of course, we are not measuring sound waves, we are measuring gravitational waves. But we can put them on speakers, and I'll do that for you. Some people might have heard this on YouTube. How many people heard the chirp sound that we played in the announcement or after that? Okay, you might get disappointed because we actually faked it a bit. So I'll tell you the truth. I'll come out clean here. I'll tell you the truth. I'll make you listen to the real signal, to that signal I showed you, that time series I showed you when you put it on a speaker. But I'll show it to you for these 2 signals. This one is not as loud, but it's longer. Because it is produced by 2 smaller black holes, then it is above the noise in our detector for almost a second before coalescence. This one is very short. It's only a fraction of a second, 0.2 seconds before coalescence. And what I'm also going to show you is a plot that shows a color. It's a time-frequency diagram, so we will have time on the x-axis and frequency on the y-axis, and the color is going to be indicating the signal over the noise, and you will see it going up in brightness because it's getting louder, and up in the y-axis because it's getting larger in frequency. That's what we expect from a chirp. So let me play this. Again, this is the first time you are going to hear the two signals, the short and the long one, twice with what we call the natural pitch. That's a long one, short one. So, that's not very musical. We had lots and lots of discussion, especially the short one. The short one is the one we made the announcement on February 11. That was the September 14 discovery. We had a lot of discussion. Should we play this? It wasn't very musical. So what we did, and we said we did it, but I'm not sure how many people listened, is that we added 400 hertz to the signals, to the sound. So now you're going to see, instead of hearing the rumble of the noise, the rumble of the instrument before the detection, you hear this 400 hertz pitch that then goes up. So that's the increased pitch. That's long. That's short. That's the one we played. So it's a lot more musical. It's not quite real, but now you know. Now we are saying that this is the beginning of gravitational wave astronomy. And we really believe that. We believe that these are observatories that are going, as long as we have them on, they are going to be measuring gravitational waves from different systems. We have already 3 systems that were black holes of these 30 solar masses forming one of 60, and then this smaller one and this candidate. What did we know about black holes before this? We knew they existed. We knew that there are these millions of solar mass black holes at the center of galaxies, and we don't really know very well how they formed. But we also know that black holes at the very beginning are formed in the explosion of stars, of supernova. Core collapse supernova are explosions of stars where the core gets very compressed and forms either a neutron star, like the stars I told you in the beginning, or a black hole. And those are a few solar masses. These are not very big stars. Or when 2 neutron stars get together, they coalesce, and then they form a black hole. But that would only be 2 solar masses. So black holes start small. And we have some evidence, not that much, but some evidence from what we call solar mass black holes from X-ray studies. If the black hole is near a regular star, then it will be accreting matter, and there will be a jet, sometimes intermittent, sometimes permanent, that is in the X-rays. So by measuring the X-rays, because of this matter falling into the black hole, we can tell how big the black holes are. And we know about a couple of dozen of black holes. They were all less than 30 solar masses. And here we had our first discovery, had 2 30 solar mass black holes, larger than ever before, forming a 60 solar mass black hole. So 1 billion years ago, there was already a 60 solar mass black hole out there. We couldn't tell from electromagnetic observations because black holes do not emit electromagnetic light, but they do emit gravitational waves. So this is really a new window to the universe that we have opened. And of course, doing astronomy usually means that we point in the sky saying there is something. Well, the problem is that with 2 detectors, each detector is like a microphone. Each detector can listen to gravitational waves coming from almost anywhere, but then that means that you cannot tell where they come from. If you have 2 microphones, like 2 ears, we can kind of localize if we are on a plane, but if you only have 2 microphones, then you don't know which direction it's coming from. So from the time difference, you can only tell a big circle in the sky, well, sometimes a small circle, but it's a circle in the sky where the signal is coming from. We can tell a little bit more because the amplitudes are not exactly the same and the phases are not exactly the same. So in a circle in the sky, this is the sky at the time of the first detection, that's a Milky Way. This is the area. We are 90% sure that the signal came from this area. But that's a huge area, that's not quite astronomy. However, there's a third detector coming online. That's a Virgo detector next year. With 3 detectors, we'll be able to do triangulation, and this is going to look a lot smaller, which I'm not sure it's going to be prettier, because I tend to think that this is a smiley and the universe was smiling at us. When we begin to see points, may not be that nice. But we are going to be taking data beginning in December with a second observing run again. We are going to take data for a few months. Sometime early next year, Virgo is going to join this second observing run, so we are going to have 3 detectors. I'm pretty sure, we can never be 100% sure, but I'm pretty sure that we're going to discover more gravitational waves from black holes. Who knows what else? The detectors, the LIGO detectors, this time will be only slightly more sensitive than they were in 01. But we'll keep working on those to make them more sensitive. And there's more coming. There's a Japanese detector in the works that we hope they plan to be finishing in 2018 or 19. India has approved the construction of an observatory where they are going to install a third detector, because the National Science Foundation paid for 3 detectors. We were going to install 2 detectors in Hanford and 1 in Livingston. But then this idea of building an observatory in a different country so that we could install that third detector somewhere else and then have better triangulation appeared, and that's what's going to happen in India. That detector will probably not begin operating until after 2024 or so. But this is every few years we will have another detector in the network adding to the signal. So this is just the beginning. But we are not just looking for gravitational waves of black holes. We are also looking for supernova explosions that who knows what they're going to look like. We are looking for periodic gravitational waves from these rotating compact stars in our galaxy. We are looking for coalescences not just of black holes, but neutron stars or neutron star and black holes, and those should produce electromagnetic radiation, so we should see coincidence, multi-messenger observations with electromagnetic and gravitational radiation. And we're also looking for noise of astrophysical origin, noise that could be produced in the very early universe, although we think that that's very, very small compared to our instrument noise, but also noise that is produced by many, many of these coalescences or many, many of these unknown transients all mixed together. So we have lots of ways of looking at the data to find lots of different signals. In fact, the first way we found our first detection was with a method that was looking for generic transients. Then we refined it with this method. But we will be looking for all sorts of gravitational waves. And this is not just a new window to the universe. This is just one corner of a window. Because I told you we have a sensitive frequency band where we measure gravitational waves that have periods of milliseconds or tens of milliseconds. But there are gravitational waves that have much longer periods. These million solar masses black holes at the center of galaxies, they would be producing gravitational waves when they coalesce that have periods of minutes to hours. White dwarf binaries in our galaxy would also be having these long periods. Those could be detected with a space detector. And there is a project like this approved by the European Space Agency that NASA is about to join too. It's called LISA, and it's very exciting. We can also measure, there are gravitational waves from supermassive black holes, 1 billion solar mass black holes that are also thought to be at the center of galaxies. Not all galaxies, but some special galaxies. And those we could measure using the radio beams from those pulsars as arms of an interferometer. If we measure correlations in the radio signals that we measure in a radio telescope, then we can use these stars as mirrors in our interferometer. So we have an interferometer that is of galactic scale. This is called pulsar timing in radio astronomy. And if we want to look for gravitational waves of the very early universe, they are largest at the lowest frequencies. Those are the most difficult ones to measure with instruments that measure distances, but we think that we will be able to, and by we, I mean the scientific community, will be able to measure these looking at the microwave background that tells us about the photons that escaped in the early universe, but measuring the polarization of those photons. The gravitational waves that existed already in that early universe would change the polarization of those photons. So when we measure those photons on Earth, which we do all the time now, we measure this cosmic microwave background, but if we can measure the polarization of that background, that would tell us about gravitational waves in the early universe. So we could tell about lots and lots of things with many different instruments. And all these things are happening. So you, especially the youngest among you, are going to be seeing news about this every couple of years. It's a very amazing time. This is just the beginning of gravitational wave astronomy. Thank you.
Beautiful. We have time for questions.
Can you tell us about LISA?
Yes, I'm a big fan of, we call it LISA, but still. LISA it was also thought about, I think, in the 70s and 80s. That was when the first concept appeared of having 3 satellites 5 million kilometers away with lasers. You don't make the laser go back and forth, but you make the laser go, and then you detect a few photons here, and you phase synchronize with another laser that goes back. That was the idea. It was in the books with NASA and ESA, the European Space Agency, but without the launching date for many years, until NASA decided they didn't have money. So ESA said, well, we'll try to do it alone, and they approved it with a launching date of 2034. So that's a bit far in the future, but the schedules have accelerated a bit since February this year. For some reason, they are all very excited about gravitational waves. So we hope that that's going to happen earlier. Also, there was a prototype mission, a mission that had one satellite with 2 masses, in which they left the masses free and measured the distance between the masses at very, very low frequencies. I mean, this is millihertz. It's very difficult to make that kind of measurements on Earth. And that measurement was so sensitive. It wasn't only better than what was expected of that prototype mission, it was about as good as what you expected to be in LISA. So with that confidence in the technology and the excitement about gravitational waves, I'm certain that this will happen earlier than 2034. By the way, that noise that you hear on the roof, that's the same noise that photons make on a photocell that we call shot noise. Okay. That's what I think when it rains like this.
Did you already finish the analysis for neutron star, and neutron star black holes in the data you already have?
Yes, actually. We actually posted that only about a month or a couple of months ago. If you go to LIGO.org, it's one of the latest papers we have posted. We didn't find any. We didn't find any binary neutron star or neutron star black hole system, but that is consistent with our expectations. We didn't think that we would get to see binary neutron star systems, at least according to predictions, until we have a sensitivity to those systems of about at least more than 100 megaparsecs. We probably need to reach 150 megaparsecs. In initial LIGO, we had 20 megaparsecs as our reach. In the first observing run, we had between 60 and 80 megaparsecs. In the second observing run, we expect to have between 70 and 80 megaparsecs. So we are close, but they're coming, but they're not quite here yet.
I want you to clarify one point that it was a bit blurred. That you say that the reason you could measure among fractions, okay, the interferometer you can measure fractions of micrometers. Is that correct?
Well, a very small fraction of a micron.
Okay, no,
yes.
okay. So that point I was not sure you were explaining it, but I understood that you said that the reason you can measure an order of 10 to minus 21 is because it's really, really far away. Is that correct? Can you explain a bit more of that? How can you achieve that kind of accuracy?
Well, 10 to the minus 21 is the estimated amplitude of certain sources of gravitational waves. And it has been the goal for many years. 10 to the minus 21 was almost a magic number we had in mind. How we achieve that precision is using all that technology that I showed you before. When I was answering earlier that another way to measure sensitivity is measure sensitivity, the reach to binary neutron star mergers. In initial LIGO, we had 20 megaparsecs. In advanced LIGO, we think that we can achieve 200 megaparsecs, 10 times farther, which means that we are going to be surveying a volume 1,000 times larger. The way we get there is using a more powerful laser. Instead of 20 watts, we have a 200 watts laser. If you have more photons, you have less shot noise, less statistical noise in the photons, less quantum noise. We used, to reduce the Brownian motion, we don't reduce the temperature, we reduce the energy losses in the system. In initial LIGO, we glued magnets to the mirrors and we had them hanging on metal fibers. Now we don't glue anything to the mirror, we glue magnets on the top mirror, and we use glass fibers that are monolithically welded to this. And all of that makes all the Brownian motion concentrate, or most of the Brownian motion concentrate on the resonances and not on the rest of the frequencies in the band. And we have much more sophisticated seismic isolation, having these quadruple pendulums instead of a simple pendulum, and having all this seismic isolation system. So that's the way we have improved the sensitivity from initial LIGO to advanced LIGO. There are ways of improving it even further. There are techniques for manipulating the quantum state of the light. That's called squeezing the vacuum. There are concepts on making the interferometers cryogenic or underground. That's something that the Japanese interferometer is going to be trying, although they're using other simpler techniques, but they are going to be cryogenic and underground. You could make it longer. There are ways of making them better. So I think that there's going to be even more advanced interferometers in the future.
I have a question over here. Thanks for the enlightening talk for us. You talked about 11,000 collaborators, if I'm not mistaken. I want to know how many scientists work in each lab. And the second question is, you told us that many more labs are going to be built. And will you have the right amount of human resources to work with it? That's a worry or not?
Well, you always welcome more experts. So there's never enough expertise, of course. You can always use better experts and more experts. There are groups of very different sizes. There are some small groups, there are some very large groups. The LIGO laboratory, for example, has 4 institutions in Caltech, MIT, and the 2 LIGO observatories, and they have like 50 people in each place. There are smaller groups. My group has about 10 people, 8 to 10 people. There are some other large groups, small groups. There are groups that have 1 person, 1 professor, or 1 professor and 1 student. So it depends on what people do. There are about 30% of the groups we have, 40% are dedicated to the technology, to advance, develop the technology for, well, they were before developing technology for these advanced detectors, and now they are developing technology for future detectors. Some of us work with the current detectors, calibrating the data, diagnosing the data. Other people work analyzing the data. What we always do is work with other people. So it's not just the people in your group. You're always on the phone, you're visiting, you're meeting with people in all the other groups, and that's why it's so collaborative. Coordinating it is a headache.
Thank you.
In this second event that you have confirmed, and as you showed, the black holes are much more or less massive, like 20 or even less, and they are exactly at the same scale or the masses where you can see X-rays and things like that.
Yes.
So no counterpart, electromagnetic counterpart on that event until now has no, at that time, no GRPs, any other telescope that had anything?
No, there
No?
haven't been any confirmed counterparts.
No.
Although, of course, the region in the sky that was also very large.
Yes.
And in several of the experiments, they actually found a supernova. But which was, with supernovas, you can only say, well, it happened a few days before. So it could have been coincident or not, but it was much farther away. But it is what happens. I mean, when these areas are so large, you look, and there is always something.
Something, yeah.
The question is
So
whether that something is correlated with your observation or not.
So I see. Thank you.
Eu queria saber se teve alguma medição diferente na chamada informação de Hawking, no momento em que as ondas gravitacionais foram captadas.
The question is whether this proves Hawking's observations on Hawking's theories on black holes. Yes. Hawking has done a lot of work on black holes. Actually, part of his earlier work was a theorem that said that when 2 black holes merge, the resulting black hole can only have certain maximum mass, which is not the sum of the first 2, because there is some energy emitted in gravitational waves and there is a minimum of energy. So that is called the mass theorem. Unfortunately, our signals are not strong enough to measure independently the mass of the final black hole from the masses of the initial black holes. We have to put it all together. So it is consistent, our observations are consistent with his theorem, but not proof of his theorem, which would be very nice, and I hope we can do it with other observations, or perhaps statistically with many observations. Another, perhaps a better known observation he's made on black holes is that they evaporate. That we don't see, because the only thing that we see is this brief interaction in space-time before the black holes merge. But the evaporation is an evaporation that happens on a long amount of time for black holes of this mass. So that we won't be able to see. We hope that we can prove the mass theorem with future observations. That would be very cool.
Recentemente o LHC tem tentado reproduzir, né, mini buracos negros, e o Hawking, uma das previsões dele, fosse que eles evaporariam. E essa medição das ondas interfeririam no que viria a acontecer na reprodução de um mini buraco negro?
I'm not sure I followed all of that. Yes.
The question was about the LHC and whether small black holes at the LHC and their evaporation would have something to tell about it after this observation. Will it help in any way clarify?
I'm afraid not. No, those black holes, these are astrophysical black holes, so they can tell you almost nothing at all about black holes that you can produce. But those experiments are things that we are all following very closely, and I at least hope that we will see black holes being created and evaporated there. The prospects are not very bright, but I'm an optimist.
One more.
Bom, primeiramente, fora Temer. Acho que esse evento é um evento muito interessante. Espero que nos próximos 20 anos a gente continue com atividades dessa natureza, mas as expectativas não são muito positivas, considerando as políticas atuais, né, de cortes de recursos para a pesquisa, né, ou de forma geral, de investimento público. Mas seguimos, né. É uma curiosidade, a minha pergunta é mais uma curiosidade sobre a possibilidade do que a gente pode enxergar, né, a partir das ondas gravitacionais, né. Hoje em dia, a gente olha o céu a partir de ondas eletromagnéticas que são ofuscadas pela matéria e bloqueadas por N partículas no céu e tudo mais. Isso vai mudar com as ondas gravitacionais, né, que tem menos bloqueios, né, pelo menos do que até onde eu consegui compreender. Então minha dúvida é, será que com o aumento da precisão desses equipamentos de medidas, além de possibilitar enxergar mais distante em, né, eventos no universo, será que a gente consegue também pegar informações que estão dentro do buraco negro, alguma coisa nesse sentido? Mais uma curiosidade.
The question is whether we can access information inside the black hole.
I'm afraid not. I wish we could. We can see the very strong curvature. Or the effect of that, right? I mean, because we see the gravitational wave at the time of coalescence, so that is produced by very, very strong gravitational fields. But everything we see happened outside the horizon. It happened due to the black hole, but the effect of the black hole outside the horizon. However, we think that we can test the theory of general relativity. So if there are theories that say that there isn't a horizon, or that the horizon is different, and if we can find clues to a theory that's different than Einstein's theory of general relativity, perhaps that will help to know what happens inside the horizon. But in principle, unfortunately, no.
Okay, let's thank Gabriela once more.
Thank you. And let me say that I thank you all for coming here, and I agree with you that it's very important that the public in general, everybody, not just physics or science students, but everybody's interested in science, and this discovery has really taught us how much everybody enjoys learning about science. So thank you all for coming.
So let's meet again in 13 minutes, sharp.